We have our definition of work. Work is equal to FD cosine theta. Remember that cosine theta term, that's what tells us is the work positive or negative. So that's where if they're in opposite directions, it's negative. If they're in the same directions, it's positive. That's where that comes from this cosine theta term. We also have the work energy theorem, where that if you do work on an object, you change its energy. We have the two types of energy. Actually, we have three types of energy. We have the kinetic energy, which is 1/2 mv squared. Again, you'll have these equations on the test, but just to summarize them. Then we have gravitational potential energy. That's mg times h. And then we also have elastic potential energy, which I'll call PES. That's 1/2 kx squared. And then the conservation of energy, which says that all of these energies, or the energy of a closed system, will always be the same. So we'll look at some different problems like this. We've worked through some in class, but we'll just look through some others. Let's just do a simple problem. I think we might have done one like this in the in-class section. Say I have an object that moves down an inclined plane. Let's say that it starts up here at, I don't know, 5 meters. That's the height. It's 5 meters. And I just want to know what is the velocity down here at the bottom. What is the velocity when it reaches the bottom? This is a conservation of energy problem. You'll certainly see a couple of these on the test where you have to calculate what is the velocity or the position of an object at a certain point in the place. Whenever you encounter these, you're starting with this principle that our initial is equal to our final energy. And you know what? Don't even think of it as initial and final. Just think of it, the energy at one point is equal to the energy of it at another point. Okay, so I have this object that's at 5 meters. We'll say that its speed is 0. It's just at rest up there, and then it slides down this incline. Then I can find the potential energy and the kinetic energy. And I want to ask myself the question, which of these is equal to 0? At the top, when the velocity is 0, what is the kinetic energy? It's going to be 0, right? And then the potential energy is just m times g times h. And then down at the bottom, where h is equal to 0, my potential energy is equal to 0. And my kinetic energy is equal to 1/2 mv squared. And then I'll just set these two energies equal to one another. So I say mgh equals 1/2 mv squared. Notice my masses cancel, and I solve for v. So if I multiply both sides by 2, and then I take the square root of both sides, I get v is the square root of 2gh. That's 2 times 10 times 5. It's 100. Square root of 100 is 10 meters per second. Right, so that tells me that this object, when it reaches the bottom, is going to be going 10 meters per second. Okay? You could do the same problem like if you were just dropping an object. So instead, let's say that I just have an object that I drop from a distance of 5 meters. It would work out exactly the same. The inclined plane is irrelevant. It's irrelevant because it doesn't have friction. But if it did have friction, and this is where it's similar to that problem number 7. The problem number 7, that part that's not on the video, it gets kind of complicated. But let's say instead I have, let's just say a section of this incline has friction on it. So there's a sticky part on it. All right, so I have 5 meters here. Or no, I'm sorry. This distance was 5 meters. We'll call this 4. Oh, wait, no, shoot, I'm sorry. All messed up here. The height was 5 meters. We'll say that this is 7 meters. And so this has a distance of 5 squared plus 7 squared. I'm going to erase all this stuff down here, okay? Okay, so you can see a test question like this. I think it might be a good question. Let's say that I have a little sticky patch on this thing It has a distance equal to, I don't know, 1.5 meters. So let's say that this sticky patch has a distance of 1.5 meters, and it has a coefficient of kinetic friction equal to 0.1. And now I want to know what is the energy of the object, or what is the speed of the object when it gets to the bottom. So what happens here is I have a certain amount of energy in this object. When there's no friction, when it gets down to the bottom, it's still going to have that same amount of energy. But because friction, gosh, what is friction? Is it conservative or non-conservative? Is that right? Non-conservative force. Does friction conserve energy or not conserve it? It does not conserve energy. That's right. So friction is a non-conservative force. That means I'm going to lose energy due to the frictional force. So whatever work is done by the frictional force, it's lost completely. So the energy of the block will equal the potential energy minus the work done by the friction, because that energy is lost. I can figure out the work done by the friction is just going to be the force, kinetic frictional force, times the distance. And that'll equal the total energy at the bottom. All right? Let's see. I wouldn't make you do the inclined plane. You could do it. Like, you could find the frictional force. You'd have to find the normal force. Then you'd have to calculate that, multiply the coefficient of kinetic friction times the normal force. That would be a little bit mean, right? Would that be mean? Y'all could do that. But I'm not going to make you do that. Okay, I'll give you the frictional force. So the frictional force, let's say, is, I don't know, 1 Newton. All right, so I say here mgh minus the frictional force, which is 1 Newton, times the distance, which was 1.5 meters. That's just that little sticky patch, how far that frictional force acts, is equal to the energy at the bottom, which is all kinetic energy, 1/2 mv squared. Now notice here that you have to know the mass. Let's give it a mass. We'll say the mass is 2 kilograms. Because the mass doesn't cancel out in this case. So I'd have 2 kilograms times 10 times h, which was 5, minus 1.5 equals 1/2 of 2 v squared. And so it's just going to be the square root of this. This goes away. Half of 2 is 1. So that's 2 times 10 is 100 minus 1.5. So v is going to be the square root of 98.5, which is a little bit less than 10, 9 point something. All right? All good on that? You want to work another conservation of energy problem? Okay. Let's do like the roller coaster problem. This is like that number 7, but without the sticky patch. Let's say that I have a track that looks like this. Say that this height is 2 meters. This height is 1 meter. And up here, the initial velocity is 2 meters per second. Have this object, roller coaster, whatever you want to think of, that's going at 2 meters per second. Oh, and this height is also 2 meters per second. And I want to know a few things. I want to know the velocity here. I want to know the velocity here. The velocity here. And I want to know how high does it come up here when the velocity is equal to 0. Okay, so the way you're going to approach this is you'll say, well, I know some stuff about this thing over here. I know its kinetic energy and I know its potential energy. And then you want to go through and ask yourself, what is the kinetic energy or the potential energy at each point? And in some places it's going to go to 0. So if, like for example here, which goes to 0, the kinetic or the potential? the potential energy goes to 0 because h equals 0 here. So my potential energy here is 0. Well, shoot, you can probably just tell me right off, what is the speed of the object right here? Priya, what is it? It's not 0, no. It's Heidi, what is it? It's 2, right. So the speed here is 2 meters per second because it's at the same height over here. So they're going to have the same potential energy, hence they're going to have the same kinetic energy. I'll write it down in just a second, but it's going to be 2 meters per second here. Here I'm going to have both kinetic and potential. Here, which one will go away? Caleb? Caleb. Yeah. No, I know my height here. It has a height. Potential only goes away when the height is 0. So which one goes away here? Kinetic, because the speed is 0, right? So then I go through, and like you'll have a figure, so you can just sort of draw on it. I know that I have kinetic energy, potential energy here. I know I only have kinetic energy here because the potential energy goes to 0. I know that V is equal to 2 here because it's at the same height as the original position. I have kinetic and potential energy here, and I know over here I only have potential energy. All right, whatever the total energy is, it's always going to be the same, the sums of them. So you can think about this as, like, if this is my kinetic energy and this is my potential energy, as I move around, they're going to shift with respect to one another. So over here, if this is my kinetic, when I come down here, the kinetic's going to get big and the potential will get small. And then up here, they'll come here, my kinetic gets bigger, my potential gets smaller because I'm at a lower height. And then up here, my potential gets big and my kinetic energy goes to 0. So the sum of the kinetic and the potential is always the same. It's just like they're shifting around, swapping back and forth. So I can compare the sum of the kinetic and the potential with the kinetic energy here, the kinetic and the potential energy here, kinetic and the potential energy there, or the potential energy there. Let's just do a couple of these. I'll do this one, and this one. Okay? How's this settling with y'all? Y'all okay with these? Pretty good. All right, let's work through it and see, because you need to be more than pretty good. You need to be, yes, I know how to do this, okay? All right, so writing the expression here, kinetic energy plus potential energy, that's going to be 1/2 m times v squared. I know v is 2 meters per second squared plus the potential energy, which is going to be m times g times h, which is 2 meters. That's this value. So I know the most about that first point on the track. So that's one I'm going to use as my initial. And now we'll write it for here. Now here I only have kinetic energy. It's 1/2, excuse me, I only have kinetic energy. That's 1/2 m v squared. That potential energy term is there. It's just 0, so I don't even write it. And then I solve this for v. Noting a couple things, or noting that my masses, they all cancel out. And then I can do the numbers here. So I have 1/2 of 4, that's 2 plus 20. I'm going to multiply this times 2, that gets rid of this half right here, is equal to v squared. So I have 2 times v is the square root of 44. It's, a little less than 7, or 6 point something. So I'll say it's about 7. Okay? And then for all the others, it's exactly the same procedure. I'm just comparing my energy in the initial state with the energy in whatever state I'm considering. So sometimes it's a little more complicated. Like, for example, for the next one, I'll look at this one right here. Because now I don't have any terms that go to 0. I only have kinetic and potential, or I have kinetic and potential for both of them. So it's going to look like this. I'll have 1/2 of m times v squared. That's that 2 meters per second that we saw over here. plus m times g times 2 meters. That's the same as what we had over here, equals 1/2 mv squared. Now that v is this one, right? I'm considering that scenario, plus m times g times what? What is my h for this second part? Here it was 2 meters. What is it? 1 meter. That's right. So I put in 1 meter. Now, a lot of it's just keeping the numbers straight, right? Because you got a lot of numbers floating around and making sure you get the right ones. And then I solve this for v. Notice my masses all cancel. They will almost always cancel, but you want to, write it all out and sort of make sure that that's the case. Because like on the previous one where we had the work, it didn't cancel out. Right? In fact, it would have canceled out. Like if I hadn't given you the frictional force instead, if you had actually had to calculate the frictional force, the mass would have canceled out because that frictional force is dependent upon the mass. But it makes for a lot of extra work. So, all right, and then I solve this for v. This is 1/2 of 4, 2 plus 20 minus 10 times 2 square root equals v. Do you want me to spend more time on that algebra, or y'all okay with the algebra? Yeah? Okay, we'll do another one like that. Hi, okay? Okay, all right. And then you would solve this for v and whatever v is. Okay? Now you do a very similar thing here. I'm not going to work because it works out exactly the same. I just say Ke plus Pe is equal to Pe, and you solve for h there. Andre, are you about to raise your hand? Oh, you solve for h, yeah. So that's what you're looking for. All right, let's do one like we did before, but a little bit different. Let's say that I have an object, and I'm trying to kick it up this ramp. Right, I'm trying to push it up this ramp, and I give it a velocity equal to 10 meters per second. Let's say that this object has a mass of 3 kilograms, and it travels up this ramp. But unfortunately, there's a frictional force that acts upon it, and it's equal to 2 newtons. I want to know how high up the ramp does it go. Okay, let's think about this. At the bottom, what type of energy does it have? Kinetic or potential? At the bottom, it only has kinetic because h is equal to 0. And I've given it a velocity. I've thumped it up. Well, you don't want to thump a 3 kilogram mass, but you push it up and you give it this initial velocity, and it goes up the inclined plane. But unfortunately, there's a frictional force that causes it to slow down, that's taking away energy. Now, there are other forces too, right? Like there's the oh shoot, no, let me think. Is this yeah, the weight. You also have to consider the weight. No, the weight is included in your gravitational potential energy. This is okay. It's all right the way we're doing it. All right, so I'm pushing this thing up, and that frictional force, because it's non-conservative, is taking away energy. You with me on this? Okay. All right. So I have this energy, and if it didn't have the friction, it would go up to a certain height. It would all be converted to gravitational potential energy. All right. But the frictional force is acting to take away some of the energy. And so what I want to know is, how high does it go up? Uh, I'm sorry. This is going to get too complicated because our height and our distance are going to be related to one another. Can we skip this one? Okay. You're not going to see anything like this. You could see something like what we did before. where you have the inclined plane and you have a predefined strip of friction and how long it's going to be. Y'all okay with that one? Should I work through like that very first one? Like this one right here. I'm figuring out its velocity. Okay, let me see if I can come up. It's going to be pretty similar, but let's, well, let's say that I have this object. Instead of starting at the bottom, it starts at the top. It has a mass of, say, 3 kilograms. Let's say that the initial height is 10 meters. And I just want to know the velocity when it gets to the bottom. But I'm going to say that there's a friction on the inclined plane. That frictional force is 2 newtons, Fk. I'm going to say that the mass instead is 20 kilograms. Make sure we have enough energy to get down. And the base of this triangle is, say, 12 meters. And I just want to know how fast is this object going when it gets to the bottom. All right. Now up top, it has potential energy. That's all that it has is potential energy. It's going to start going down this inclined plane, and I want to figure out how fast would it be going. Now, if there was no friction at the bottom, it would all be converted into kinetic energy. So this would be at the top, this would be at the bottom. And it would be mgh equals 1/2 mv squared. The masses would cancel, and then we would solve for v, the root of 2 times g times h, which is going to be 2 times 10 times 10 is the root of 200. Which is 14 meters per second. Right, that's how fast it would go if there were no friction. But because I'm losing a little bit of energy as it goes down the inclined plane, I'm going to deduct that from this potential energy. So my potential energy minus the work that's done by the frictional force is going to equal the kinetic energy at the bottom. Okay? You with me? With me? Okay. So now it works out very similarly. I have mgh, that's mg times 10 meters, minus the work done by the frictional force. That's going to be the frictional force, which is 2 newtons, times this distance. I'll need to figure out this distance. 10 squared plus 12 squared, square root of 244, which is 16 meters. Right, that frictional force acts along 16 meters. That's equal to 1/2 mv squared. Now the mass here you need, so it's 1/2 times 20 is v squared. Putting 20 here as well. So that's 20 times 10, 202,000 minus 32 divided by 10, the square root of that. And I get 14 as well here. 14.0. This was actually 14.1 meters per second. So it's going a little bit slower, not much. Okay? All right. Need to know how to find work due to a force. I think that y'all are you okay with that? We sort of had that on the last test, but we'll see it again as it comes up. Conservation of energy, calculating kinetic energy, knowing how it changes. You want to look at some old test questions? Yeah? Okay. All right. Okay, this one's a little bit different. Let's look at number 15. We haven't done one like this. We did in the in-class section, and y'all might have seen it in the online section. But I have this, spring. Has a spring constant of 900 newtons per meter, and it says that the hand compresses it to 0.2 meters right here, negative 0.2 meters. What is the elastic potential energy stored in the spring? Well, how do I find the elastic potential energy of a spring? Remember that one? What- K. Right. So what is my K? What is K? Right. That's my spring constant. So K is 900, and then what is X? Right. It's the 0.2 meters. Right. So my potential energy of the spring is 1/2 kx squared. That's how much energy is stored in that spring, which is 1/2 of 900 times 0.2 squared. I could have carried the negative, but it'd go away anyway, so I just dropped it because it's a squared number, and the negative squared is 1. Right, so it's 450. I get 18 joules. All right. Could I ask a similar question where what is the velocity of the block, or what is the speed of the block at x equals 0 meters? Okay, so when I compress this spring, I push this spring back over here, I give this, there's energy stored in that spring, and when you let it go, it's going to give that energy to this block. And so when it comes over here to the equilibrium position, I'm going to have all that potential energy is converted into what type of energy? Kinetic energy. So in order to find the speed of the block at x equals 0 meters, I would say the potential energy initially, the initial potential energy, that's this 18 joules, is going to equal to 1/2 mv squared. So I'll have 18 joules equals 1/2 of the mass times v squared. Notice here that the mass does not go away. Often the mass does go away when you're just dealing with potential and kinetic, gravitational potential and kinetic energy, but when you're dealing with springs, that mass never goes away because the potential energy of the spring is not dependent upon the mass. It's only dependent upon K and the compression or the elongation of the spring. So be careful of that. Remember that that mass doesn't cancel out. Sometimes you'll have the mass. If you need the mass, you'll have it. But sometimes when you don't need the mass, you will have it too. And, just be aware sort of what you're dealing with. Be careful with your algebra. Just don't go canceling stuff out willy-nilly like you sometimes do. Okay? All right, so I didn't give you a mass. Let's say it's 4 kilograms or whatever, just for a number. And I get 18 divided by 2, square root of that gives me the answer, which is 3 meters per second. You'll definitely see a problem like that. So you're going to see the roller coaster problem. All right, you're going to see the friction problem, how much work is lost, how much energy is lost by the frictional force. You're going to see an elastic potential energy problem like this. You could also see a Hooke's law problem. That was the previous problem. Simple though, you're just asking what is the force. Hooke's law says that the force on a spring is equal to K times X. Remember, when we gave this in the book, it was actually negative Kx. Usually though, when I'm calculating the force due to a spring, I just leave off that negative because I know what the direction that the spring is pushing. And so I usually just leave off that negative and don't worry about it. So here F is Kx. It's just going to be 900 times 0.2. So what's that? 18 newtons, I think. 900. No, 180 newtons. So it'd be 900 times 0.2 times 18. Yeah, 180 newtons. Is that going to be to the left or the right for this spring? This is the force that the spring is pushing on the object. Will it be to the left or right? It's going to be to the right. Right, so the spring, the hand is pushing this direction, but the spring is pushing back in this direction. So make sure you read that carefully. Let's see, I had a question previously. Let's take a look at it. What is the force exerted on the block by the spring? Well, you have to be careful here. The force exerted on the block by the spring is going to be, we calculate it to be 180. Is it going to be positive or negative 180? It's going to be positive because it's to the right. Uh, Whereas the force exerted by the hand is going to be to the left, but the force exerted by the spring is to the right. That works out in the math if you do the Hooke's law with the negative. F is equal to negative kx, negative 900 times negative 0.2. It comes out to positive 180, and that's your answer. Rhea? Why is that? It's just we decided left is negative. Mm-mm. Right, yeah. Yeah, always we take negative, left to be negative and right to be positive. No, is left is negative, right is positive. Okay? Um, it's because we use a right-handed coordinate system. If we used a left-handed coordinate system, it would be the opposite way. All right? Okay, let's take a look at some of these others. You know, there's some conceptual stuff like this, like what is the work done? It says that a force is applied to this child. Her speed is 3 meters per second. Her previous speed was 1 meter per second. Was that positive or negative work being done? Right, because I'm speeding it up. I'm giving energy to it, so it's a positive work. I know we had that on a previous test a little bit, but you could see it again because it's still related. Um, some stuff about just the relationships between the energy and the x value, like this one, for example. How does the work required to stretch a spring 2 centimeters compared to stretch it 1 centimeter? Is it same twice or 4 times as much? I'm doubling x, so the work is doing what? It's quadrupling, because remember work, let me write that out. Here I have x equals 2 centimeters. Here I have x equal 1 centimeter. I want to know how much work is required to stretch it 2 centimeters over 1 centimeter. How much more work is required to stretch it twice as far? Now, the elastic potential energy is 1/2 kx squared. But remember by our work energy theorem that this is also equal to the work. Whatever energy I give that spring, I have to have done that same amount of work. So if I double the distance, it's squared, so I quadrupled the amount of work. So C would be the right answer. You'll definitely see several questions like that asking you to think about how these variables are related, the work and the energy and all that business. Sometimes it's a quadratic relationship with V and the kinetic energy, X for the potential energy. Sometimes it's a linear relationship, like for mass or the spring constant. So for example, if I increase the spring constant by a factor of 2, that would just increase the work by a factor of 2, because it's a linear relationship. Okay? All right. You'll see some, oh, this is momentum. Anything else in particular? So you'll see one or two couple questions like this probably. What would y'all like to do? That's it for that chapter, really. We can, if y'all want, I mean, we have 10 minutes or so, we could go into momentum, which we're going to get to tomorrow. You want to see a little preview? Momentum, listen, these two chapters are probably the easiest chapters of the whole semester. All right, so let's try to master them so you get perfect scores on the test for this material. I don't want to say they're easy, but they're certainly easier than the other chapters, uh, largely because they're not vectors. Okay, so we're going to get into momentum tomorrow. Momentum actually is a vector quantity. In the momentum, we're going to use the capital letter P. Is that right? We use capital P? No, we use lowercase p, I'm sorry. We use lowercase p is equal to the mass times the velocity. So these are vector quantities, mass times the velocity. It has a unit of kilogram meters per second. No fancy units, just kilogram meters per second. And a couple of things that come about with this that you'll encounter problems for momentum are impulse problems and conservation of momentum problems. We'll go over both of these, and you'll see them in your homework and what have you, but you'll see problems from both of these. Let's just do a conservation of momentum problem, and then we'll wrap it up. All right, so conservation of momentum, similar to what we had for conservation of energy, says that the initial momentum equals the final momentum. This applies whenever we have collisions. So when you have collisions between two or more objects, the products of the mass and the velocity will always remain constant, the sums of all the velocities, mass and velocity. So let's say, for example, I have two objects. I have a ball that is 2 kilograms, and it has a speed of, I don't know, 3 meters per second. It's going in that direction. And then I have another ball, we're going to do 1D, of another ball that's going in this direction. Let's say it's 4 kilograms, and it's going at 1 meter per second. What I want to know is what happens to these after they collide. So they're going to come together and collide. And let's see, I'll go ahead and tell you, I know that one of them, just the way that they bounce off one another, I'll say that the 2 kilogram ball bounces off and goes in the other direction at 2 meters per second. And what I want to know is, what is the velocity of the 4 kilogram ball? It's a collision. They bounce into one another. One of them bounces off and goes at 2 meters per second. I want to know what is the velocity of the other one. Okay, a couple things to note here is that this is a vector quantity. So when I'm adding things up, I need to remember the vectors. I need to remember what's positive and what's negative. So for example, here I have a positive speed, I have a negative speed. Here I have a negative speed, or negative velocity, and I want to know what is the velocity here. Okay? I also know that the initial momentum has to equal the final momentum. To find the initial momentum, it's going to be the product of the mass and the velocity. That's going to be 2 kilograms times plus 3 meters per second plus 4 kilograms times minus 1 meter per second. So that's the initial momentum, just the product of the mass and the velocity. And this is equal to the final momentum, which is going to be 2 kilograms times minus 2 meters per second plus 4 kilograms times V. I solve for V. So I have 6 minus 4. The initial momentum is 2 kilogram meters per second. This is negative 4 plus 4V. 6 equals 4V. 3 halves, that's 1.5 meters per second. So what that tells me is, first of all, this came out positive, so this is going to be going in this direction at 1.5 meters per second. You will see a couple problems, 1 to 2 problems that are conservation momentum, probably more like maybe 2 to 3 that are similar to this. We're also going to see different types of collisions. Like we'll see what we call um, perfectly or elastic and inelastic collisions, and then also perfectly inelastic collisions. Um, I don't want to get too much into that. We'll get into it in class. But um, in all of those, momentum will be conserved. Sometimes the objects will stick together, and then they'll both have the same velocity. We can do that here. So let's say that in this problem, we'll take the same one. Instead of what we have here, let's say that the two objects stick together. So my 2 kilogram and my 4 kilogram, they stick together. Velcro or whatever on them. They just stick together and then they slide off together at the same velocity. What direction do you think they're going to slide? Are they going to go to the left or the right? Why do you think to the left? No? Well, that's good reasoning. It's not right. Why do you think to the right? Because it's going quicker, right? So here, like both of you have good reasoning. You happen to be right, but you're not necessarily. I think it's sort of by luck that you got it right. I don't know. Anyway, like you said, this is the bigger mass, so it seems like it should dominate, right? But it's going slower, right? This one is a smaller mass, but it's going faster. All right, so which one's going to win? The one with the more momentum will win. This has 6 kilogram meters per second. This one only has 4 kilogram meters per second. All right, so this together, these have a net momentum that's positive. That means if I make them stick together, they're still going to have a positive net momentum. So it'll look like this. I would have 6 minus 4. That's 3 times 2 minus 1 times 4 is equal to 2 plus 4 kilograms times V. Notice this is exactly the same way we work this other problem right here, except that they now both have the same velocity, so I just combine those masses. So this 2 is equal to 6V. V is equal to 1/3 meter per second. My speed will be to the right, 1/3 meter per second. But you know what? If, for example, let's say that this speed was -2 meters per second, then Heidi, you'd be right. It'd be going not to the right, but to the left. Because now look at the momentums and how they're different. If this was going 2 meters per second, this momentum would be -8. And this momentum would be 6. And then the net momentum would be not 2, but it would be -2, which means I go to the left. So you'll see a couple of those. Those are two types. You'll probably see one of each of those, actually. The The first one's called an elastic collision, and this one's called a perfectly inelastic collision. Few terms. Let me throw a few terms at you that you'll need to be familiar with. There's different types of collisions. You have elastic, inelastic, and perfectly inelastic. In an elastic collision, both energy and momentum are conserved. In an so an elastic collision, not many elastic collisions, because remember, for energy to be conserved, what type of forces have to be at work? For energy to be conserved, what type of forces? Conservative or non-conservative forces? Conservative. That's what they do, right? They conserve energy. And the only types of forces that are truly conservative are what type of forces? Gravitational force and one other, the electric force. Field forces, forces that do not require contact. So elastic collisions really only occur between gas particles, basically, in real life. Because gas particles, when they collide, they don't actually touch. Don't know that? They just sort of bounce off one another without touching because of the electrical charges. So elastic collisions are largely between gas particles or between charged particles. Now we approximate some collisions as elastic, like billiard balls. They don't lose much energy when they bounce off of one another because they're just so hard and they don't give very much. So we approximate that as an elastic collision. In inelastic collisions, only momentum is conserved. And this is every other collision. Everything that's not elastic is inelastic. So it could be anything. It could be a car crashing into a tree. That's an inelastic collision. And momentum is conserved. The initial momentum will equal the final momentum. And in a perfectly inelastic, it's inelastic, but they stick together. That was like the one we did before. It's just sort of a subset of the inelastic. Momentum is conserved. You have two objects. They're moving, and then they stick together and move in one direction together, just like that previous problem. So we'll get into that nomenclature. What's tomorrow? Friday. We'll probably get into it on Monday. Houston, you might have already seen. I don't know if you've gotten that far ahead. A little bit, yeah. So momentum is this is about the whole chapter on momentum. We have one other little section on impulse, which has to do with the forces that are involved. But that's it on chapter 6. Really just conservation of momentum. I said it's not easy, but it's a lot easier than chapter 4. So if you didn't do well on chapter 4, you should expect to do a lot better on this. But it's still going to take some work. Okay? All right, folks. Thanks for coming out. Not sure if anybody would come. But y'all always come.